Okay, so in this lecture, I'm going to go over in a little bit more detail, the empirical Bayes calculations for the baseball problem we talked about earlier. So in the, it's this example one here in the notes. Okay, so a lot of the material is written out there, but I'll just go to the whiteboard here and go through the key steps. Okay, so remember that the idea is that we've observed data on baseball players. So maybe we want to estimate the batting average. So theta J I'm going to use to be the batting average for player J. And let's say we observe XJ, which is the number of hits. So that's our data. And NJ is the number of at-bats. Okay, so of course we're going to assume that XJ given NJ is binomial. So each time you go up to hit, each time you go at bat, you have a theta J probability of getting a hit. Okay, so of course the maximum likelihood estimate for theta is just the number of hits that you observe divided by the number of at-bats. And we noted that, that particularly if the number of at-bats is small, then this estimator might be quite noisy, and maybe we could do better by a Bayesian kind of use where we had some kind of prior on theta J. So let's suppose that theta J were beta with some parameters A and B. That would be, so that's going to turn out to make the computations easy, because the beta is the conjugate prior for the binomial distribution. But okay, so now the key idea behind empirical Bayes is to actually estimate A and B, that is, estimate this prior from the data that we've got. And so I guess I'm going to assume here that we've got lots of observations. So J equals 1 to, I don't know, M maybe, just to avoid N again. So visually, what you can think about going on here is that we've got, got parameters A and B here, and then each of the thetas, theta 1, is being drawn from that beta distribution. And then the x's that we're observing are noisy estimates of the thetas, or they depend on the thetas anyway. I guess I'm going to treat n as fixed and given rather than as random. So, sorry. So the intuition here is that when we're estimating theta 1, let's say, all the other data here tell us something about A and B. So we could use all these other data to estimate A and B, and then we could use that as a prior on theta 1. So, but actually we're interested in all of the thetas. And so we could do that by a leave one out type idea, where we use, when we're looking at theta 2, we use x1, x3 up to xm to estimate A and B, and then use that as a prior for theta 2, and we could do it one at a time in a leave one out kind of way. But it's a lot more convenient to simply do it in 2 steps. Firstly, estimate A and B by maximum likelihood, say. So that would be, so the likelihood for A and B is defined to be the probability of the observed data, which are the x's, given A and B. And I'm going to, again, n is implicit here. I'm going to assume that n is always given, so it's implicit there. So this is equal to the product, over j of p of xj given a and b. That's because these are assumed, the data on different players are assumed to be independent here. So that's equal to the product over j of the integral of p of xj given theta j a and b, p of theta j given a and b d theta j. Okay, so that's the likelihood. So in fact, this term here, the p of xj given theta j and ab, given theta, it doesn't depend on a and b. You can, the picture kind of suggests that. Maybe maybe I should, in my original model here, I should have maybe put a given theta here. Maybe that would have helped. Let me put that in up here at the top. Okay. And then maybe it's helpful to be a bit more formal about that as well. Okay. So this, sorry, going back to this term p of xj given theta j and a and b, it doesn't, this term here, it doesn't depend on a and b anymore. Once you know the batting average, the a and b become irrelevant, so we can get rid of those. Okay. And then, in fact, this is, so this first term is binomial, and this term is a beta. So actually, the distribution that you get from this integral is called a beta binomial distribution. So it's a product over j of beta binomial. Let's call that xj, which with parameters that depend on a and b. So I'll just write it like that for short form. But so this doesn't have a simple analytic expression for the MLEs for a and b, but it's got a simple analytic expression for the likelihood. So you can use a numerical optimizer to optimize over a and b, for example. Okay. And actually, of course, we'd probably do that by taking a log first. It's easier to, because then you get a sum over j, a log likelihood. So it's usually nicer to work with those sums, numerically more stable. So that's step one, and estimate a and b. So the idea again is using all these data here x to estimate a and b, and then when estimating x1, we're going to use the estimated values of a and b, let's call them a hat and b hat, and the value of x1 to get the posterior distribution for theta. So 2, we're going to do inference for theta j, let's say, based on the posterior, which is p of theta j given a hat, b hat, and xj. So actually, this is just a very simple Bayesian calculation now, because the prior on theta is beta distribution by assumption, and the data xj are binomial, and the posterior for theta, if you use a beta prior and a binomial likelihood, is a beta as well, because it's conjugate. Okay, so this is a beta distribution. In fact, it's beta a hat plus xj and b hat plus nj minus xj. So that's really easy. Okay, and so if you wanted a posterior mean, for example, so when I say do inference, you can do anything you like. Maybe you want to get a point estimate. One way of getting a point estimate is to use a posterior mean. And so the posterior mean here, for example, E of theta j given a hat, b hat, xj would be equal to a hat plus xj, that's this part, divided by a hat plus b hat plus nj, which is the sum of these bits here. And that's a b here, okay? So what you can see here is that this estimate of theta is actually a compromise between the prior mean, which is a hat over a hat plus b hat, and the data mean, if you like, or the MLE, xj over nj. So this posterior mean will actually lie in between that prior mean and the MLE. Okay, so that second part is just straightforward, simple Bayesian inference, and it's this first step that's really gives the empirical Bayes its name, because you're estimating A and B from all the data. And so in doing that, you're kind of making an assumption that in some sense the x's or the theta, well, you're making an assumption that thetas all come from the same prior distribution. So that's one assumption that's going into this kind of model. We don't have to make that assumption, but actually, you know, relaxing that assumption, it's a bit tricky. But let's suppose, for example, that our data set consisted of pitchers and non-pitchers. So the pitchers are the ones who don't specialize in batting, they specialize in throwing the ball. In some leagues, they bat as well, but they might be expected to bat worse on average. So you might say that their A and B for the pitchers might be different than the A and B for everyone else. So you might do the analysis in two groups. So if in that kind of, that would be an easy way to kind of avoid assuming that everyone has the same A and B, is say, well, there are some groups that are kind of special and we're going to give, you know, so we could do the analysis in two groups. And in fact, in the blog post we talked about, Dave Robinson takes out the pitchers to avoid, you know, making that assumption. But in general, you might imagine that A and B, you could even imagine that A and B, you know, that you're uncomfortable assuming A and B is the same for everyone. You want a different A and B for each person, depending on some covariates about that person. Maybe their, I don't know, their height might come into it, their arm length, their weight. You might want to allow that A and B to depend on those things. So that's a very interesting thing to want to do and very natural, but actually, you know, it's not that straightforward to decide how to do that. So it's not impossible to do that kind of thing, but you'd have to build more complicated models. So we're going to focus on this simple case, which is already pretty useful. And you can think about it as kind of an approximation that ignores those kinds of effects where A and B might depend on some covariates. Or if you didn't know the covariates, for example, in this case, we don't have access to the players' heights and weights. So in that context, it's quite natural to assume they have the same A and B. So that's kind of the first concern you might have, or something you might think about. A second issue that you might think about is this fact that A and B are just being estimated and then plugged in. So people who critique this empirical Bayes approach, one critique they might give is that actually you don't know what A and B are. So when you're looking at the uncertainty in this posterior distribution on theta, this uncertainty here, and you've plugged in A hat and B hat, you've ignored the fact that A hat and B hat were actually uncertain. And so that underestimates the amount of uncertainty in theta. And so whether that matters or not really depends a lot on, you know, how much uncertainty is there in A and B. So if you look at the baseball example, M is pretty big, and in the data set that Dave Robinson gave. So you have a pretty large amount of information about A and B, and probably your uncertainty in an individual's batting average, particularly one who's only been at bat once or twice, is, you know, it's not driven primarily, your uncertainty is driven primarily by the fact that you don't have much data, not by the fact, that is, you don't have much data on that particular individual, not by the fact that A and B are kind of uncertain. You have a lot of data to estimate A and B because you're using all the players. Now, in some settings, M might be small, and then you might be more worried about that situation. And the last thing that we've already kind of touched on this is, you know, it could be critiqued for using the data twice. So, you know, in a way, you first estimate A and B here using all the data, and then you look at inference for theta 1, let's say, given x1 and A hat and B hat. So you kind of used x1 when you estimated A and B, and you used it to compute the posterior. And so my answer to that is, well, that's a small effect in the sense that, you know, we could have left, you know, if you wanted to really be careful about addressing that, we could have left x1 out when estimating A and B, and just used x2 up to xm to estimate A and B. But it wouldn't have really made much difference because, you know, x1 itself contributes very little to the estimate of A and B. And it's so much more convenient just to do it in 2 steps that that's what we do. So again, that relies on the m being kind of large, and that's an assumption here. Okay, so that's the outline. In the notes, there's a lot more details about some of the math, but that's an outline of how the empirical Bayes approach would work in this setting, and also maybe some of the potential concerns and answers to those concerns that you might have.